Hello, and this video is on lesson 4-2 step functions and absolute value functions. This begins on page 61. So the first thing we're going to do is learn about step functions. So we want to graph step functions and absolute value functions, and we also want to describe the attributes of these functions. A step function is a piecewise defined function whose value remains constant throughout each interval of its domain. Work with your group on items 1 through 3. Use your group discussions to clarify the meaning of mathematical concepts and other language used to describe problem information. With your group or your teacher, review background information that will be useful in applying concepts and developing reasonable descriptions and explanations. Let's take a look at this here. A piecewise defined function with a constant value throughout each interval of its domain is called a step function. Constant value. Well, let's take a look at this step function right here. And what do you notice about this piecewise defined function? Here are my function rules, and here are my domain restrictions. Now, these function rules, they're missing something that we've seen in the previous step, piecewise defined functions. The function rules have always had a variable along with them, but notice that instead of having variables in our function rules, we have constants. And so, how do we even begin to graph this? Well, you can set up a table, and you have your x and your f of x. And since our graph starts at -6, we'll start at -5, -4, -3, -2, 0, and going all the way to 4, 5, 6. Alright, there's our table. Now, notice that we can draw our walls. In this case, something different about this. We have a wall at -3, a wall at 2 as well. So we actually have two walls here. So remember, we create our walls with vertical dashed lines. I can create my wall here at -3, and then I have another one at 2. Okay, let's take a look at the first function rule. -2 if x is less than -3. Well, first of all, let's look at the domain restriction. X is less than -3. Which of these numbers in my table are less than -3? Well, it's only going to be -4 and -5. So these numbers I'm going to plug into the first function rule. But notice I don't have a variable here. What does that mean? Well, this is going to be your answer. The constant is basically what your answer is. Since you don't have a variable to plug in, nowhere to put my inputs, it already gives me my output, which is -2. So -2 is going to be my output, and here are going to be my first order pairs. -3, oh, that's supposed to be -5. -5, -2, there's my point right there, and -4, -2, there's my point right there. Now notice that this is going to be the same points at -2. This is actually going to be a horizontal line, and it's going to continue like this for all x values less than -3, which means it keeps on going and going to the left. And the way to represent that is by using an arrow. This -3 right here, x is less than -3. All these numbers to the left are less than -3. But notice it's going to hit that wall right here, and once we hit that wall, we have to figure out, do we use an open or closed circle? Well, in this case it's going to be an open circle because I have less than. So there's my open circle right there. Open circle. Okay, So that's the first part of the graph. Now let's go ahead and take a look at the next function rule. Here we have 1 if negative 3 is less than or equal to x, which is less than 2. So which of these numbers in my table are less than or equal to 3 are, well, actually greater than or equal to, between negative 3 and 2 basically. Greater than or equal to 3 but less than 2, and it's actually going to be negative 3 all the way to 1. So these numbers I'm going to plug into the second function rule. And again, for all these inputs, I don't have any variable to input it in, so my output is basically 1 for all of these. 1, 1, 1, 1. And so if I go to my graph, I have negative 3, 1. Notice this falls exactly on the wall, so I have to be careful here. If it falls exactly on the wall at negative 3, what type of circle am I going to have? Well, this is less than or equal to, which means I'm going to have a closed circle. So closed circle right here. And then if I graph the other ones, you can see how, again, we have a horizontal line. And when I connect these dots, it's going to keep going until I hit this wall at positive 2. And when I hit positive 2, I have less than, which means I'm going to have an open circle. So there we go. There is the graph right there. Alright. Finally, the last function rule, 3, if x is greater than or equal to 2. Well, what values in my table are greater than or equal to 2? Well, it's basically all the numbers here, and it just keeps on going. So that means on this side of the graph, I'm going to have my outputs be all 3. And so have 2, 3. Now this falls exactly on the wall, which means I'm going to have to pay attention to the inequality, greater than or equal to, which means it's closed circle. And so I can go ahead and graph all these points. And notice that it's for all values greater than or equal to 2, which means that it just keeps on going, so I represent that with an arrow. So there we go. There is the graph of the step function. Now, why do we get a graph that looks like this? Well, because we again, in our function rules, we have constants. This is why we have all these constants. All right. Now, there's something important that I want to point out here. This will be important in your embedded assessment. Basically, what I want to ask you is, what is the domain of this graph? What is the domain? So let's go ahead and take a look at this really quick. The domain. Remember, I like to use the idea of elevator doors to find the domain. So don't confuse a single step as just one. Don't confuse just a single piece of the function as a single function. We have to look at all of this together. And so when I open this left elevator door, I'm not going to stop here. I just want to open it up so the whole graph can squeeze through. And notice, since I have this arrow, this elevator door just keeps going and going. And so for my domain in inequality form, I'm using the variable x. I'm not stopping this door on the left, so that means I'm going to negative infinity. And we always use less than as our inequality. Now, when I open this door to the right, again, I'm not going to stop here, here, or here. I'm looking at the whole graph in its entirety. And notice at the end I have an arrow, so that means I keep on going and going, and it goes off to positive infinity. So here's my domain. From negative infinity to positive infinity. So this is the inequality form. Set notation is going to be where we have our brace x such that x is an element of the real numbers. This is a shorthand form. We can also could have used this, but what the book is basically using is this notation right here, where this inequality form and this shorthand form are basically the same thing. So that is set notation. We also want to use interval notation. Basically, you take your smallest value, comma, your largest value, and since we have infinities on both sides, we have less thans. That means we use parentheses. So here's the inequality. This is the set notation, and this is the interval. And in the embedded assessment, it also asks you for the range. And the range is a little bit tricky. The embedded assessment, page 99, it asks you for the range in set notation. And so that's what we're just going to do here. We're going to write the range in set notation. So that means I'm going to have my curly brace, y such that. Now, if I use the idea of elevator doors here, this time since it's the range, I'm using vertical opening elevator doors, and as you can see, I would probably stop my bottom elevator door here and my top elevator door right here. And so my range would be from -2 to +3. But this would work out if I had a continuous line going from -2 to +3. But can you see that I have these gaps in between? So it's not going to be just from -2 to +3. I'm going to have to put that, again, I have to use this notation here. So y is an element of the real numbers, but it's saying that y is equal to -2 because it falls exactly on -2, and then or y is equal to, can you see how it falls on +1? And then finally, or y is equal to 3. So because the range falls on these numbers right here, -2, 1, and 3, this is how I would write my set notation for the range. That would be it. Okay. So that prepares you for the embedded assessment. Let's see. Okay, so we have this right here. I think I should clear this first. So we're going to be looking at number 6. This is a really special piecewise type of function, piecewise defined type of function, which here are the function rules right here, and there are the domain restrictions. Now if you can see, let's go ahead and draw our wall first. So here's our wall, right? It's acting as the y-axis. And let's take a look at the first function rule and the domain restriction. -x if x is less than 0. Okay, so for all my values that are less than 0, basically these values right here, I'm going to take those inputs and plug it into the first function rule. So if I take -3 and plug it into x here, what I get is -3, and 2 consecutive negatives make it positive, so that's actually +3. And when you do the same thing for all of these, you get positive numbers as well. So we can go ahead and graph these: -1, 1, -2, 2, and -3, 3. Now notice that these are for all values less than 0, so this keeps on going and going and going and going, and as you can see, it continues that pattern. But once it hits that wall, which is at 0, 0, you're gonna have to stop right there, and in this case it's gonna be an open circle. So we'll just create an open circle right there. Alright, let's read the second function rule. X, if x is greater than or equal to 0. What numbers here are greater than or equal to 0? Well, 0 itself, and also any numbers larger than 0. And notice when I take these inputs and plug it in here, it's basically x, which means the number itself. So if I plug in 0 for x, what's going to be 0? 1 gives me 1, 2 gives me 2, and then so on, 3. And so, as you can see, start at 0, 0. Now this falls exactly on the wall at 0, 0. And since I have greater than or equal to, it's going to be a solid circle. And notice I keep going and going and going and going and going, and it continues that pattern, so I basically draw an arrow. So here's my piecewise defined function here. This is called the absolute value function, which has the shape of a V. What are the domain and range of the function? Well, use the idea of elevator doors here. You'll be able to find what the domain is quite easily just by seeing where do they stop so the graph can squeeze inside. And to find the range, you have to find where the top and bottom elevator doors are going to stop using elevator doors that move vertically. Alright. Now this is interesting. Does the function have a minimum or maximum value? What do they mean by that? Well, basically, it's kind of similar to, you kind of find the answer when you're looking for the range. When this top elevator door is opening up, it's not going to stop because these arrows are pointing basically up, and it just keeps on going and going and going, and it never stops. And so, is there a maximum value where this elevator door is going to stop? No, it just keeps on going and going and going. So there is no maximum. Now, what about the bottom elevator door? Is there a minimum value where this elevator door is going to stop at? Yes, there is. And can you see how it stops here? And that is my lowest value where my elevator door stops at. And it stops at 0. So what this means is that I do have a minimum, and it's going to be y equals 0. Why is it y equals 0? Because remember, for the range, you're just looking at the y-axis. And since we're talking about the y-axis, we're talking about y values. And where does this elevator door stop at? It stops at y equals 0. Alright. What are the x-intercepts and y-intercepts of the function? Well, that's pretty just by looking at the graph, you can see where it intersects the x and the y-axis. Describe the symmetry. I think that's self-explanatory as well. The function f of x in item 6 is known as the absolute value function. The notation for the function is f of x equals absolute value of x. The sharp change in the graph at x equals 0 is the vertex. So right here, that is the vertex. This is going to be called the vertex, the point at where both lines meet. Use the piecewise defined function of the absolute value function to evaluate each expression. Alright, so you can use this information here in order to evaluate each piecewise defined function. So if I have f of negative 14, my input is 14. 14 is greater than 0. So that means I'm going to plug it into this function rule, and so my output, if my input is 14, then my output is going to be 14. Simple as that. Oh, actually negative 14. That means if it's negative 14, I'm not going to plug it into this function rule. I'm going to plug it into this because negative 14 is less than 0. So if I plug in negative 14 in for x, I get, let's see here, I get minus negative 14, which becomes positive 14. So f of 14, negative 14, is equal to 14. Now, there is a simple trick. Basically, you can take the absolute value of any number, and this is basically what it's asking. What is the absolute value of negative 14, absolute value of 8, absolute value of 0, absolute value of 2 minus square root of 5. Anytime you have a negative inside the absolute value, it makes it positive. That's always going to be true. Anytime you have a negative number inside the absolute value, the answer is going to be positive. Anytime you have a positive number inside the absolute value, the answer stays positive. So negative turns into positive, positive, it keeps it positive. If you have 0, well, the answer is always going to be 0. And here we have 2 minus the square root of 5. This one's kind of tricky. Is this a positive or a negative number? Well, the 2 is positive, so the 2 is going to stay positive, but this minus square root of 5, it's negative, so whatever is negative, we're going to change it into positive. So here's the absolute value. I may want to check that. Let me check that real quick. Let's see here. Yes. Oh, isn't that interesting? So the answer is minus 2 plus the square root of 5. Okay, so in that case, using your piecewise defined function is very important, because you have to determine, first of all, is this number, let's see here, my piecewise defined function is going to be x, negative x, if x is less than 0, and it's going to be x if x is greater than or equal to 0. We have to figure out 2 minus square root of 5. Is that a positive number or is that a negative number? So you may have to use a calculator, but in this case, what it seems to be, this seems to be a negative number. So they plugged it into this right here, and what you basically do is, when you plug it in there, you have that negative in front of it, and then this negative gets distributed, and so you come out with negative 2 plus the square root of 5, and so that's why it came out with that answer. Okay. And then on page 64, I had you do this for homework. Questions number 14 and 15 are very similar to page 99, number 5b, A and B, I believe. So those, I really definitely emphasized these questions, 14 and 15. Alright, thank you for watching.